Good afternoon, everyone. My colleague Daniel Sanchez, together with the other members of the team and I, have developed a framework that allows to run virtual machines using Wolfram Language. During this presentation, we are going to show the advantages that have been made, as well as the machines that have been implemented using this framework. Why virtual machines in Wolfram Language? Well, because Wolfram Language is future-proof, and that makes it the ideal platform to develop a working environment that allows the preservation of landmark computational systems, as well as the execution and debugging of the software that was developed for these computers.
Right, and which virtual machines have we considered so far? So there are three basic types. And the first are the abstract machines. These are the machines that you can find in a new kind of science book. So far we've implemented three of them: raster machines, deterministic finite automaton, and non-deterministic finite automaton. And in the future, we would like to have more of the machines that appear in that book. Another type of virtual machine is the process virtual machines. These are the machines that are intended to execute code in a platform independent way. And these are your Java virtual machine, or most programming languages that have a virtual machine entering this category. And the one that we included in this project was the Ethereum virtual machine. And finally, another type of virtual machine we've considered are the processors virtual machines, and in particular, those that are some vintage, right? We've included 4 of them so far, and these are the PDP-1, 8, the Intel 404, and the MOS 6502. But before diving into each of these processors, I'm going to make a really quick demo about the symbols of the package. So first we have virtual machine, which is a function that receives the name of a virtual machine that's implemented in the framework, and it creates an instance of that machine. So it returns a virtual machine object, and you have here some information about the object. So with that object, just like with any other object in the language, we can query some properties. And in this case, I'm asking what's the state of the processor at that instance. So I get an association with the keys corresponding to the components, registers, flags, etc. And their values are the contents of those components. And finally, the last main symbol is the virtual machine execute, which takes a virtual machine object and applies some kind of command. And in this case, this command is loading this list of integers, which you could interpret as a program, or a binary, and load it into the memory. Okay, so now we are going to go through each of the processors.
Well, this was the first computer we implemented, the PDP-1. And this computer was developed by the Digital Equipment Corporations. It was its first computer, but it was also the first computer that was oriented to the user interaction. It was released in 1959 with an introductory price of $120,000 and occupied something like 17 square feet of floor space. Using the framework, we can provide some basic information about this computer. For example, you can see in this dataset that it had a word size of 18 bits and an address size of 12 bits. And it also had a standard main memory of 4,096 words, which was upgradable. In this image, you can see a page of the manual of the computer. It contained the instruction set of the computer, but we also have this information in the form of datasets, and we can use it And for example, we can calculate how many instructions the machine has, and we could take a random sample. And using the framework, we can see, for example, the mnemonics of each of the instructions. We can see the full name and the operational code and how much time, and a small pseudocode of how the operation works. And as a demo, we are going to run the Spacewar game, which was first developed for the PDP-1. The PDP-1 was the original hardware for the first version of this game. This game was implemented by Steve Russell in 1962. And for example, in this cell, you can see how to create an instance of the computer. And then we are going to load the binary of the game into its memory. And then we are going to, to set the program counter value to the initial position. After that, we can see, for example, the representation of the screen, which shows nothing because we have not still run the program. But then we can run 500,000 steps. And while that, you can see here the two ships of the game as they are pulled to the center of the screen because of the star gravity, which is in the center also.
Okay, so next is the PDP-8. It was also another computer from Digital Equipment Corporation. It was launched in 1965, and this is a picture of the brochure that came out in that year. And it is known as the first commercially successful minicomputer. Compared to the PDP-1, this machine is much smaller, so it can fit in the back of your car, and much cheaper. It still shared lots of similarities with the PDP-1, so you can see here that it also has a front panel where the user can interact directly with the machine, see the contents of the registers. And so yeah, we are going to see a better example later on. More basic information. Costed $18,000 at the year, and it was and there were over 50,000 units sold of this mini computer. Another important characteristic is that its word size and address size was both 12 bits. So, and also their basic memory size, just like the PDP-1, was 4 kilobytes long. I should mention that its memory cycle time was 1.5 microseconds compared to the PDP-1's 5.35 microseconds. So overall, this was a smaller mini computer and faster. So given its success, this machine had lots of models or versions, and we have another dataset here of those versions, and we have its introduction dates, withdrawal dates, prices, and pictures of their front panel and how it evolved over time. Okay, instruction set. So the instruction set is what it's what gives the PDP-8 its name. So the machine has 8 instructions, and you could call this a single instruction machine. So the word of the each of the word contained the full information about the instruction. So you can see here that the 3 bits of each word determine which operation. So there are 8 operations in total, and the remainder of the bits are the operands. So in most cases are the address of the operands and whether to do indirect addressing or not. So okay, it has 8 instructions, the machine, and this is a simple data set with basic information about those instructions. Okay, so now let's see a example, which I should have spoiled. Okay, so the idea is that I'm going to run this, load this program into the memory and play with this. So I'm going to create an instance of the PDP-8. I'm going to load into memory this list of integers, just like we did with the Spacewar. And this list corresponds to the compiled or the assembled version of this listing. And then I'm going to execute it from panel. this is the front panel that I get. So it's an interactive, dynamic model. So you can see here that each of these bulbs here corresponds to the contents of the registers. And here we have another panel with showing which instruction I'm executing right now and in which phase the machine is in. We also have 12 switches here, and these switches were used by the users so they can interact directly with the machine. And we're going to see an example. And these remainder switches are the manual, are used to do manual operations on the machine. So instead of using instructions, you could press these switches and change the state of the machine. Okay, so the program has already been loaded, and to verify this, I'm going to set the address 0010, and I'm going to load it into the program counter with the load address. So it appears here. And then I'm going to use the examine switch to see that this has been loaded correctly. So I press exam, and I see here in the memory buffer that the 7300 has been loaded. And this indicates that this is an operate instruction because these are part of the operate instruction group. The exam also increased the program counter in 1. So now I can use exam again to see the subsequent memory locations. So I press exam and I get 1020, which corresponds to this instruction. Again, 1021. And the last one is the hold instruction, 7402. Also, forgot to mention that this subroutine adds 2 numbers located in this memory location 20 and 21 and stores the result in the accumulator. So if we add these 2 numbers, we will have overflow. So this link will be set and the result will be stored in the accumulator. So I'm going to load back again the start of the program. I'm in this location and I'm just going to run it. So it was quite fast, but yeah, the link bit was set and the accumulator stores a 1 now. Okay. The next microprocessor, it's the Intel 404, and it's considered to be the first commercially produced microprocessor. So that's one of the reasons we chose this processor. And it was launched by Intel in the year 1971. And you can see here a picture of the announcement. And if you can see here, the 404 had other siblings. And it's because this 404 belonged to a family of chipsets called the microcomputer set 4. And in this family, we have the 4001, which is the ROM chip. You can see a picture of it here. And besides having a ROM buffer, it had an input and output port. So that's kind of unique. We have the 4002, which was the RAM chip, sorry, and it had a output port. This is the one. The 403, that's not always needed, but it's useful. It's a shift register, and the 404, which was the processor. More basic information, the introductory price was $60 at the time, and it was designed by Federico Fagin and Mash Arkhov from Intel and Masatoshi Shima from PCCom. The processor had data width of 4 bits and address width of 12 bits. Okay, this is a picture taken from the data sheet, and it shows the 14.5 instructions the processor had. We have this as well in the form of data sets, just like all the other machines. So there are 45 of these instructions. And here we see only 5, and we see the name, the bit pattern, which is, we wanted it to look exactly like in the manual, and some short description of each of these instructions. Spoilers. Okay, so here we have another example, and this time I'm going to use a debugger that comes with this machine. And the idea is I'm going to load the assembled result of this program, and I'm going to load it into the machine. So I'm using this function, a resource function, which assembles this program and outputs a byte array. Okay, so I'm going to create an instance of the Intel 404 and specifying the number of ROM chips we want. So we want 2 chips, and I'm going to use that to execute the debugger. This is, it looks a bit weird in that notebook. It should look more prettier. So I'm going to load the byte array here, and I'm going to put this into memory, into the ROM block. So you can see here that the contents of the ROM have changed. This is somewhat like a hex dump. And this program, as it says, it computes the 4-bit AND of 2 numbers, and the first number is taken from the input port of the ROM, the first ROM chip. I will try with 15 here, and the second number is taken from the second ROM chip, and I will put 7 here. Okay, so now everything is loaded, so I could step by step it and see which instruction I'm executing, how the registers are changing, or I could just animate it and see the result. The result is stored in the RAM chip here. I can stop this, reset, change the number. Let's see, 7 with 7 should output 7, and I get the result. So yeah, this is it for the Intel 404.
And so our last processor will be the MOS 6502. This microprocessor was developed by the MOS Technology company, and it was proposed as a simplified, cheaper and faster version of its predecessor, the Motorola 6800. This microprocessor was released in 1975, and it is very well known because it was the core element of very popular console games such as Atari and Nintendo, and it was also the central unit of computers like the Apple II and Commodore 64. We also have its basic information in the form of datasets. And here, for example, you can see that the data width of this microprocessor was 8 bits and its address width was 16 bits, and that it operated from 1 to 3 megahertz. In this table, you can see a very quick summary of the instructions. You can see that each instruction is composed of one operation and the operands, and from the operands, the microprocessor deduces which addressing mode it is using. We also have a dataset with these addressing modes, which you can have them using the framework. And we also have another dataset to see the operations. We can calculate how many operations the processors can do, and we can take random samples of them to see the mnemonics, the full name of each of them, and a pseudocode to explain how the operation works. And as a demo, we're going to play the snake game. I don't have to tell you what the snake game is. I'm sure many of you are familiar with this game. So following the same procedure with the other processor, we are going to first create an instance of the MOS, and then we are going to load the binary of the game into its memory and to indicate the start address to the program counter, and then we are going to start to play. In this panel, you can see that we have buttons to run, to stop, also to reset the game. We are going to use this input field to simulate the pad, and we can start playing. And that's it. No, we play and we have fun using this processor. You can stop the game and continue.
Right, so these are the machines we've implemented so far, but we would like to not stop there. So we would like to have many more processors and notable software and other machines in the framework. So that's why we would like to launch this. We want to launch this virtual machine project that has some objectives, and these are to have a framework where enthusiasts and other people can add their other machines, other vintage processors or new machines, and a repository of machines software that people can download and play around with. And really built a community of people interested in these machines, in their preservation, study, exploration, etc. And we need tools, right? For example, if you've noticed, every machine we've implemented so far had their own set of custom peripherals, but ideally we would have generic or reusable peripherals, and we would connect these peripherals with each machine without changing much of the code. And finally, if we want to run, write code, assemble code, we need really assemblers and disassemblers for each of these machines. Before finishing, we would like to extend our special thanks to Brian Silverman. He has shared with us his knowledge and expertise throughout the duration of the project. We've met lots of times, and he has given us lots of great advice. So thank you, Brian. And just as for the last slide, I'm here leaving the project contact information. So you can email us at virtualmachineproject@wolfram.com. Send us feedback, some ideas, so yeah. And finally, if you want to start playing around with what we've done so far, we've added this to the virtual machine, to the new Padlet repo. So you can follow this link, and if you have Wolfram Language 13 and up, you can use the resource object and install this. So yeah, this is a picture taken from the page. Okay, so maybe we should start with the questions. Yeah, let's see the passable. Right, running Doom today? Not Nikolai, not today, not yet. Or Star Trek, no. Right. That's the reason we want people adding their own machines, right? We couldn't possibly add all the machines ourselves. And I know there are people that really are into one particular machine that they are much more knowledgeable than us. So that's why we want to launch this project and have some kind of workflow where people can add their own machines. Have you, or do you plan to explore the Infocom C machine? Oh, sorry. I have no idea what's just, yeah, but I guess it would be possible. Right. What Christian said. So this will be a version 13 feature. Yeah, so it's not coming with the main language, right? But it's coming with the Padlet repository. So you can install it using this resource object, actually, in case, okay. Right. So that's an important point, Jesse. Performance it's crucial, right? Especially with these machines, with the processor machines, because these machines are meant to be run, are needed to run constantly, as opposed to abstract machines or the Ethereum virtual machine that just need to compute some, to crunch some, what's the word? I don't know, contract, right? These are needed to constantly be running. So yes, we wanted to explore, we tried exploring a compile, and we need to do more work on that. But right, okay, I think I understand. So you want to compile Wolfram language code to PDPA code. That would be interesting. According to Wikipedia, given that it was so simple, the PDPA, its instruction set, it led to significantly larger code. So we'll see how pattern matching is implemented in the PDPA. How can we hack our reality VM and Jack? Thanks, Daniel. Right, it was right. The MOS 6502 was used by vendor. Yes. How is several of the demos of, okay, how is the input-output layer handled? Several of the demos so far contain excellent recreations of vintage machines, control panels, and displays. It is implemented as a separate layer on top of the basic processor memory. Right, so the example of the PDP-8 and the PDP-1 and in the Intel 404, those are peripherals, let's say, or input-output layer that comes with the machine. So it comes as a virtual machine command or property, right? The only one that we didn't, where we didn't do that is this snake here. So the virtual machine of the MOS 6502 is just the instruction set and memory of 64 kilobytes. And on top of that, here there's some code that we used to build a layer of input-output on top of it. So, right, so this byte array of this snake is taken from a page that explains how this processor works, and it's not using really the interrupt mechanism of the machine. So we are doing some tricky, some tricky stuff here. But yes, in this case, this is a layer outside the virtual machine framework. So that can be done. How fast are these emulations in comparisons to the original hardware? Right, yes. Yeah, so it's performance was not our first priority. Of course, we had to have in mind performance, right? But we wanted first to write a cohesive framework for all the machines that we implemented. And the idea is to explore more about function compile and how to compile these machines. Yes. Here you are just looking at a visualization of the virtual computer's memory and treating that as the video output. Have you replicated any video chips? Right. Have you replicated any video chips such as the NES PPU? Yeah, maybe Stefano wants to say something about the PPU.
Well, he's right. We are just rendering the computer's memory. We didn't have the opportunity to emulate the PPU of the NES. It was underdeveloped, but then we decided to leave it for later. But we will soon do that too.
Right, and that other chip could also be considered another virtual machine, right? So we need to figure out how to work with different virtual machines. So that's for the future. My computer was the TI-9940. Is this in the works? No, but what's in the works is the framework for adding more machines. So maybe you could add it yourself, Edmund. Do you downclock the ops based on the original runtime time? No, we do track the number, how long each instruction takes. And if we are successful in making every instruction run faster than what the manual says, yeah, I guess we could. We had the idea of downclocking the execution time of the instructions. Yeah, that would be nice. What practical applications are there applications are there in Wolfram Language for these virtual machines? Yeah, we had in mind, I think, two main applications, right? The first would be to do some preservation of these machines, the software, have them in some kind of computational form, be it in data sets or what else? And the second one was education. So we would like some, I don't know, classes or courses to use this framework to teach how these machines were used in the past, how they evolved. Roughly how many instructions per second can a modern laptop execute using virtual machine? Roughly Yeah, I don't know the answer to that. I will have to check it. My first computer was the IBM 60. Nice. Yeah. So yeah, as Christian Pascal said, please send us feedback, ideas, thoughts to that email. John Fultz. Thanks, John. Right. We had to dive deep into the front end to make these different panels and input output layer work. So thanks. And yeah, run this on the Raspberry Pi. Yeah, we need to test this on more platforms, but in theory they should work. Soon there is going to be a quantum computer backend. Maybe we can do it as a virtual machine too, right? We need help then. Generally speaking, what's involved in adding a new type of machine? Yeah, exactly. Yes, that's a good question. That's not set in stone. So we've classified the machines we added, but we need to do some more, I don't know, assumptions about the machines given their type to improve how these machines are added into the language. So yeah, in short, there's not really much about specifically the type of the machine. I'm saying that the emulation need to have the same performance. I'm just curious how close it gets thanks to the sheer speed of modern processors. Right. We did try to have fast Wolfram language code, but without doing much, it was the PDP one at first was almost 1.5 slower, but then we reduced that time. So yeah. Okay, that's the end of the questions. I think yeah, our time was, yeah, yes. Okay, yeah, I'm over the time. So yeah, thanks for coming by, and hopefully we can talk again later.
Thanks, everyone.
Thanks, Stefano. See ya.